And we're starting the recording for online. Just a few housekeeping rules for people online, essentially. So if you video and microphone off, so Etienne or me will be looking at the conversation. If you have any questions, just raise your hands or write to the conversation, and we'll be able to answer your question at the end. And people here will probably do conversation, and there will be some open time for the question. I'll take this off. Okay. All right. So we are now in the first course of the CopPhil training course. Well, actually, there was one introduction that maybe you attended to in October, which was an overview of the CopPhil program. Now we are starting the theoretical courses that we will be that you will see for all of the services that we are developing in CopPhil, and then we go into more practical session on EU services, and finally on application. Okay, so this is all you have here, an overview of the overall program of the CopPhil training course. So you may be aware that within CopPhil we are working essentially on three main services. One is on ground motion, one is on land cover, but which also includes forest and crop, and one is on landscape habitat. So this is the overall program. We are now in starting the fundamental. Do you see my? So we are here in these fundamentals of the language, starting the first the round of training of courses. A quick word on the Moodle platform. So you will all the content that you will see today, you will be able to find it under the CopPhil Moodle platform. So I will leave this slide also at the break and at the end, so you can go to that. So under this courses.copphil.filsa.gov.ph, you will find all the content of this training, of the previous one also, the training one, and all the following that will all be stored and archived for you to access online. Then you will see when you have to register to this platform. It's a free registration, and when you will be registered to this, you will have access to all the courses in the Moodle platform and to get back to all the information. So again, for people or for your colleagues that may have missed this one, they can also go back to the courses. So this is for the Moodle, and then all these training courses that we are providing on the CopPhil will allow you to get some certification at the end. So this is the process to get the certification. The first one would be to apply for the training course, which you have probably done already, attending the course, which is what you are doing now. And then at the end, there will be like a course certificate, which will be delivered after answering a few questions on the quiz for each of the sessions, and to allow us to see if all the contents were well understood. And then you will be able to do to get one certificate of attendance for each course and one certificate of participation for the whole training course. For this one, and again, I will share this later at the break longer. For this first course, this is the link that you will need to follow to access to the certification process. I will leave this earlier when we at the break. Is there any question so far on the process, Moodle platform certification? Should we go now into interesting stuff? Okay. To change. Sorry, I need to. Yeah. Yes. Okay. Continue the agenda. We will now start the motivation and overview. Understanding land cover and land use. So in this first session, which will be just really introductive, we'll go through Earth observation using satellite technology, introduction to the type of sensor that we use in land cover, a few examples of applications, and also some introduction on the impacts of the data selection when you want to do some land cover application. Okay, so introduction to satellite for Earth observation. So this is actually still a recent technology because the first satellite was a Russian satellite Earth observation which was launched in 1957, and we got the first images of Earth observation in 1960. So this with the satellite, now you can get a global Earth coverage. It monitors only the surface, so you cannot see like deep in the water. It's also an information that you get in real time, and since then, it also gets allows to get access to a long-term and continuous data. For example, for the sea surface temperature, which is a parameter that you can get with the Earth observation, we have data since 1984. There are a few limitations for observation, which are the distance, some obstacles that you will see, some weather conditions, we will also see that, and some unfair conditions for the sensor. So the observation satellites depends on several parameters, which is the orbits, also the type of sensor that you have on your satellites, and we'll go through this. Some interference also with some radio signal, and the atmospheric condition is a very important parameter. And you can also build some database using multi-mission, getting several satellites and combining data from several satellites to get some multi-mission products. So satellite data is result of a complex processing. It's not easy to handle at first, and we'll try now to get you some first insight on how to watch this data. Just to give you an overview, there are today more satellites on Earth than there are islands on the Philippines. So there's a lot of satellites around the Earth. More than 1,000 is specific for Earth observation, dedicated to Earth observation. And among these satellites, these are just a few examples of the type of satellites that are used for the land cover specifically. So you will see that sensors, different type of sensors, different types of satellites coming from different agencies. So we have like the American satellites, European satellites, Japanese, all the main space agencies have their own satellites, but we'll now focus in this particular course in program on the satellite from the European system. So now if we start to look at what is a satellite image, so we have two types of sensors. We have what we call the active sensors, which are more like SAR images, and we have also the passive sensors, which are the optical images. You see the difference on the picture there. These are two images taken from satellite. On the left, you have the SAR image, which is usually where you find it in black and white. For the Copernicus European constellation, we will be discussing about the Sentinel-1 satellite, which is the name of the SAR satellite of the Copernicus constellation. And for the optical images, or the passive sensors, then you can see that it really looks like a picture, like a photograph, and it's easier to interpret. And for the Copernicus European constellation, we'll be talking about essentially Sentinel-2 for the land program. Okay, but this one is not working. Huh? Huh? This one is not. Okay, bah oui, mais Lâche. Okay. Or if you can't, like, I'll go with this one until the battery is down. So the main difference between the active and passive sensors is the way they act. So the passive sensor, which is the optical sensor, it's easy to understand. It's actually they are passive receiving. So they are only receiving the signal that the Earth is coming back to them, is sending back to the sensor. So it actually needs some light, and it's only receiving the data. While the radar sensor, so the active sensor, is sending some information to the Earth and then getting the information back. So depending on the type of sensors, you are able to go through a wide range of electromagnetic waves and frequencies. And depending on the frequencies and the type of active or passive sensor, then you get different type of information. A few words on the passive sensors, but then Etienne will go really deeper in the next session. So as I mentioned, it's a reception of waves, of electromagnetic waves. It can see through usually from visible thermal, infrared, and infrared to the range of the wavelengths that these satellites are able to see. The advantage, as we mentioned already, is that is easy interpretation. So when you see the image and you see the image on the right, you can easily interpret and know what is on your image. There's also less correction to apply because it's cleaner data. It's also you know already what you are looking at, and you can also do some possible combination of bands to calculate some indices, and this is what we will be talking also later. But the main inconvenience for this one is that it's sensible to cloud. So as we mentioned, because it's passive sensor, it needs some light, it needs some sun, but also the signal cannot go to the cloud back to the satellite. At the contrary, or complementary to the active sensors, the radar images, so it's emitting and receiving the electromagnetic waves. It also works in a different way, in a different range of wavelengths. In terms of radar sensors, as example, we also have type of sensors on Earth observation satellites, which are like the altimeters. The altimeters are sensors that are actually used to measure the ocean height or the ice. And here for what concerns Earth today, this is also used on river and lakes and to detect some changes. We do SAR. SAR means synthetic aperture radar in SAR. We also have type of sensors to measure the wind, the scatterometer. So all these are of the family of the radar images. The advantages of this type of sensors, it's contrary to the optical one. It can see through cloud, and this is very important. This is the main advantage. But then it also has some inconvenience, and in particular, it's more difficult to interpret. You can see the same image here in black and white. It's a bit more difficult to know what you are looking at, and it needs more data processing. And in general, when you want to build some projects from satellite, this is not straightforward. So the satellite, of course, it allows you to have a global coverage of the full Earth, which is very interesting. You can also produce some applications at regional or local level. But usually you have to, on your satellite data, you also want to add some models. You also usually want to combine it with in situ data. some expert analysis, knowing what you are seeing, and with combining everything, so the data, the in-situ data, additional data, the models, to do expertise, it will allow you to produce some added value produce that will be able to use in several applications. A few examples now. So use case and practical applications of the satellite for the land cover, combined with all this other data. This is an example here, actually coming from the CopPhil project that we are conducting now. This is the first map of the results that was calculated. So here you have on the map an image showing you the different classes that you can find on Earth or on this particular area. So you can see in red that you have built-up areas. In yellow, you can identify perennial crops. All this area comes from a computation that we'll go through in the second part. And if you combine this land cover classification or land cover analysis of your ground, of your satellite image that represents your ground, and if you combine this, for example, with some models of digital elevation models to get the topography, you can identify and where are the areas prone to some flooding information, flooding events, identify also the landslide risk terrains, detection also fire susceptible areas. If you see that the vegetation from what you are calculating is dry. And it can really help you also in several other applications, such as to tracking the urban expansion, to monitor the critical habitats, preserve biodiversity hotspots. So there's plenty of things that you can do when you apply all this expertise on an image. A few application cases for the land cover and plus. So for another example is the forest management. So when with the satellite, applying the correct model and in these calculations, and also using a time series of images, so succession of different images, you can actually detect the changes in the forest, and meaning the areas of deforestation. From one map to the other, you will see where are the changes, and you will be able to identify through the calculation of indices where is the changes and where the trees have been deforested. Another example, more related to agriculture, this one, with the satellite and applying some calculation of indices to your Sentinel-2, to the optical images in this case, you can identify the different type of vegetation, because all the different crops that you will see will show a different light, will have a different color, different characteristics, different seasonal stage of development, everything. So everything, all of this gives a different color actually to your lens, to your image, and it's easy. It's a way to go through the information and to characterize the different varieties of crops. Another use case on this, you can also detect the tree density, and with the tree density on your crops, then you can estimate the crop production intensity. So you can go from one dense to like low density to high density. It helps you to understand where is your crop going to be more productive. Another type of use cases that we are actually not working on specifically on CopPhil, but this is also some use cases that you will be able also to develop, because all the data and the main results of the CopPhil program will be to allow the Philippines to get the access to the Sentinel-1, Sentinel-2 data on the Copernicus CopPhil mirror site. So it means that there will be like a data center. There is a data center being installed in the Philippines that will allow to get easier access to all the satellite information. So from this, we are developing some services, some use cases, some three examples on three services that have been selected. But there are also other applications, and one of them is the water management and irrigation. with an example on Cambodia, but it works, of course, on a global coverage. With the radar imagery this time, you are able to monitor the change and the evolution of your water bodies. So this is a big lake here, the Tonle Sap Lake, and you see from one season to the other the extent of water, which is different. And on the right here, this is an example of identification of crops that will be partially irrigated. So they will send back some information on the moisture content that would be different. To go deeper on this type of irrigation and forest, essentially, there will be specific courses that will also start, and I'll do that. I'll tell you at the end about this information. But you will be able to go deeper into some specific contents for the crop and for the forest, essentially. So another example of what you can do with the satellite Copernicus data, when there is a flood, the satellite data allows you to rapidly or to assess easily and on the global coverage the extent of the flood and thus the impact of the flood in communities, in the agriculture, in urban areas, in all the domains that you need to take care of. And the last use case, just also to illustrate the power of the satellite data and the Sentinel data to really a large range of application. The Sentinel-1 data, so the radar data, is also used especially on the sea, on the observation of the sea. And with this, it allows to detect some pollution, so oil spill detection, but also detecting vessels. And with this, you can combining the detection of the vessels and some pollution that happen in the area. Combining this with some vessel identification system, combining all this data, you actually can set up some applications, some services to detect illegal activities, crossing the vessels that are emitting, the ones that are not, but that you can see on the image. Then it allows you to have an overview or a good view on the activities that are going on at sea. Okay. So this is just to give you some ideas of where you can go at the end when all the process is applied, and what type of application can the satellite help you to manage. I just want to conclude this first part on giving some information on introduction to the selection of the data. You see there's many types of data, different sensors, different wavelengths, different size also. So it's very important when you select your data for your
You have been muted, ma'am.
Hello, Marion. You might need to check the audio, please, Etienne or Marion. Thank you.
Is it better now?
Hello, it's back. Thank you.
Can you hear me?
Yes.
Yes.
I'll leave this back. Okay. Yeah, for the one that arrived later, there's a paper for attendance that circulates in the room. So ask for it, please. Sorry. Okay, so talking about the selection of appropriate data. So the geographical definition of your areas, but also the temporal definition of your area. Do you want to have something which is instantaneous, real time? Do you want to represent monthly, yearly situation? What is the quality of your final project? Because depending on what type of quality, then you have different choices to make, in particular in the resolution. What is the thematic definition of your final project? Does it have to respect some our existing norms to be similar to other projects that you want to compare with? What will be the availability of the auxiliary data? Do you have in-situ data to validate your system in one area or the other? And also the calendar of project availability. Do you want to update this on a daily basis, weekly basis, yearly basis? All these questions are important to have in mind when you're starting an application and when you're starting to use the data. And of course, we did not mention this yet, but the available budget. So the Sentinel-1, Sentinel-2, Sentinel-3 data, the Copernicus program are offering free data. So all this data will be accessible for free. So this is a good argument, but sometimes you need, for some reason, to have like very specific access to very high resolution, for example. And in this case, you would probably have to go to commercial agency that will sell higher resolution data. Just to illustrate the different resolution. So here on the left, you have a Google Earth image, right? Which we call very high resolution data with a pixel resolution of about 1 to 4 meters. Then the same image, but seen by Sentinel-2, will give you a resolution of between 10 15 meters, which can be enough if you want to identify in your urban area what would be the vegetations, the urban areas, the trees, all this information. And then if you look again at your information, but using Sentinel-3 data, the resolution is then 300 meters. So it's really like a step back. It's good to represent the large scale information, but then maybe not sufficient if you want to detect small scale fields. So type of availability of data, we've seen this at the beginning, but from an optical image and a radar image, you will see the same thing, and you will not have to apply the same type of processing. And I just mentioned earlier also the data costs for free data of the Copernicus program and the commercial missions provided by other providers. And finally, so just to give you also an idea of the data volume that it will represent, because when you want to process some data, you also have to store it, to store the image that you want to process. And depending on the data type and the analysis that you require, if you want one image, a time series, everything, this can represent a large amount of data. A few numbers, a few figures for you to take away. For the very high resolution data, or like less than 1 meter resolution, one image can be from 1 to 50 gigabytes, so it can be very big. Sentinel-1, Sentinel-2, Sentinel-3, for one image, it will be 1 or 2 gigabytes. And to conclude again, so as I already mentioned, so the access to the Sentinel data will be provided through the Copernicus CopPhil mirror site, and there might be also some program related to or training related to the access, particularly to the how to access the data on the CopPhil mirror site. So this will be done in the course of the year, I presume. And when you want to analyze the data, what type of tool that you're using, we see Etienne will show some example of a tool, IOTA tool, but there's also GIS software such as QGIS, QGIS, SNAP, OTB, which are common tools that you use to work on the satellite data. And this is just to conclude, really, on my last slide, to give you just a view on the project which is being developed on the CopPhil specifically. So this is on the right an example of the land cover produced by Namibia on the Luzon region, and we are trying and we are intending to reproduce this type of map with the CopPhil tools, and we're working also with Namibia on this and other stakeholders that are that will be then able to process this map and to update the frequency of process of this map. Just what we'll be delivering on this service, particular service on land cover. So we intend to be able to produce one map on a yearly basis, updated every year on a yearly basis. Main input will be Sentinel-2 data. And it will respect also, in this particular case, the classes, so the classification, which is already used by Namibia. And we will respect this and allow a higher frequency of revisits and of recalculation of this map. Okay, so this was for the introductive part. I don't know if you have any questions on this. There, yes. I think yeah. For the person online, I will remove. For the flood, usually it's active, so it's the radar data. Well, you can do both. Usually you can do both. You can use Sentinel-2 optical and Sentinel-1 radar. It depends on what you want to see. Like the map that we see here, I think it's from Sentinel-2. But you can also look at changes more easily with the Sentinel-1 radar.
Yeah, and maybe if I add something, it's when there are floods, there are really bad weather very often. So SAR images us to have an image whereas there is cloud cover or not. So that's why it's very often.
How about the land cover with the last part? If you use supervised.
For the Namibia land cover, I'm not the one who did it, so I cannot go into the details. I know there is some machine learning in it, but for the land cover service we are producing for CopPhil, yeah, we are using machine learning, and we'll present it just later.
So I often download in open access different Sentinel-2 data. And most of the time I download 30 by 30 minutes. And then I see that the Sentinel by 10.
Yes.
How can we do that?
Okay, I will repeat for the people online. So the question is, there are some download, if I understand, you download, if I understand correctly, 30 per 30 meter resolution images. From which sensor exactly are you using for your process? For Sentinel-2, whereas we presented it was 10 meter, but it depends on the band that you use, meaning that depending on the spectral band in the visible and near infrared, it's actually 5 band in 10 meter resolution. Some band at, if I remember correctly, 20 meter resolution, and in some other band it's 60 meters. It depends on the spectral domain. in the thermal domain, it will be 60 meter resolution. So yeah, it depends. So I don't know if it's image per image or another end product are you using, but maybe this end product for this specification has 30 meter resolution. You're welcome. Okay.
Okay.
Okay. Hello everyone, nice to meet you all. So I'm Etienne Ducasse, and I'm a PhD. I have a PhD in remote sensing, and I'm glad to present you the basics for remote sensing and more details on what we do for CopPhil and in the data processing we do for land cover mapping. Okay. So, yeah, it's the first slide. Okay. Remote sensing, what it is, basically, it's the interaction, the study of the interaction of electromagnetic signal with the matter, specifically the Earth. And what is an electromagnetic wave? It's, as I said, as Marion presented earlier, component of the light, for example. And we'll have two main parameters, which is dependent of the speed of the light, which is the frequency and the wavelength. And depending on the wavelength, you will have different interactions with the matter. So as you see, you will have the. I will just. Okay. So it goes through the UV and UV to the infrared for the optics, and then the radio waves for radar signal. As Marion showed it earlier, there are two kinds of sensors. Passive sensors, which study the reflection of of another source of electromagnetic signal, which is the sun, through with the Earth, and active sensors. So an example of passive sensors are hyperspectral, multispectral, and thermal. I see I just switched active and passive sensors. I'm sorry for that. With some differences. The problem with the main challenge with this kind of sensor is that we have to take care of the atmosphere. So that's why the most of the studied spectral ranges from these passive sensors are between the visible and infrared range, because there is a lot of transmittance through the atmosphere. There is no absorption through the atmosphere in these wavelengths. And also there is some active sensors, such as radar or LiDAR. We will not address LiDAR in this presentation, but radar is very widely used for remote sensing as well of the surface. So I start first with some information of remote sensing in the optic domain. So optical remote sensing in the optic domain, as I told you earlier, makes use of visible, near infrared, and shortwave infrared sensors to get image of the Earth surface. And it uses the study of the interaction of the reflected signal in this wavelength with the Earth. And the advantages of optical remote sensing, it's quite a kind of easy interpretation of images because it's very close of what an human eyes can see in the visible domain in particular. And also it has a great richness because we can have also some invisible at the human eye spectral wavelength, and so it adds some spectral information in it. But there is also some disadvantages, such as it uses the sun as a source of illumination. So you have to take care of this. For example, depending on the angle of illumination, we have some shadows, and you will have to address also some problems due to the atmosphere. For example, take care of the absorption in some wavelength of by the atmosphere, and to manage, for example, clouds which are present. And also, as every sensor, satellite sensor, it's a compromise between resolution, temporal visit, and spectral richness, which allows us to have these images. So if we go deeper in this, the main variable we study in optics remote sensing, it's reflectance. Reflectance is the part of the reflected signal which is registered inside the satellite. It's a fraction. So if you see here, there is an incident radiation. So basically the sun, which goes through the Earth surface. And as you can see, there is some different interaction with the matter. So part of it is reflected. So it's a part we studied with remote sensing. Part of this is absorbed through the materials. And part of it is transmitted further into the material. So in order to conserve the energy where the surface received it, the energy which been received, it was the energy which been transmitted plus the one which has been absorbed and one which has been reflected. So in the end, for one wavelength lambda, so if you see the reflectance plus absorbance plus transmittance equals 1. So, and it's only this part which we are going to study. So let's go on to see what reflectance does exactly. So as you see, part of it, part of the electromagnetic signal is through the materials. And so it will be really interesting to see the reflected materials, to see what's left of it. And each material is different. It will have different interactions, and so different spectral signatures. As we see earlier, reflectance achieve each wavelength plus the absorbance plus the transmittance equals 1. So we'll have a percentage here of reflectance at each wavelength will depend on each materials. And so it will depend also of the field of light, which is function of the wavelength, the polarization, and the angle of incidence of the light source, of course. So you see here some example of reflectance spectra for dry source. Here you have only one absorption at around 2 micrometers. Vegetation, which is most widely used with a big increase of reflectance from visible to near infrared, which is widely used. We'll see later for indices. You'll see also that when the soil is wet, there is drop in global reflectance. And globally, water has really low reflectance spectrum. So when we studied this reflection spectra, it's also interesting to look at spectral indices, which are formulas which allow to get more information of the condition of Earth's surfaces. And as it normalizes the signal, it will have some interesting effects, such as, for example, it will drop the negative effects due to atmospheric condition, for example, and the differences of measurement conditions. Also, it will allow comparison between different data sets as it normalizes the signal. And also, it will be much more easier to use at different spectral bands for example, because from 4 or 3 images will go into 1. So here's an example of the most known, and you probably know it. It's normalized difference vegetation index. So we'll see here a spectral, the reflectance of green grass, actually. And when we look, a little bit more closer to the visible and near infrared domain, we see there is a big increase between the red part and the near infrared. And so for this part, we can calculate the NDVA, which is near minus red on near plus red. So if you look at the images, how does it look? So, for example, the example here is using Sentinel-2 sensor over Sudan. So you will have on your left the red image. Here you see the Nile going through. And on the right there is near infrared images. And when you look at the index produced, you'll see in green the higher value of vegetation index, and in red the lower value. Here we are in the bottom of the valley of the Nile, so we see a lot of vegetation. But if you go a little bit away, it will be a lot drier. Another example using green and shortwave infrared. It's the MNDWI, which is the water index to study water. And this example was taken after a flood in Sudan. So you see in the valley of Sudan a lot of water on both sides of the Nile. Fun fact, it's also used for snow detection under the name NDSI. So normalized different snow index. Another one example, which is from Greece from last year. There was big fire in Greece, and so there was the possibility to see it through satellite remote sensing. And so using near infrared and short wavelength infrared, you can calculate the NBR, which is normalized burn ratio. And here in red, you can see the burn area. So using this formula, of course. So it is of a big interest, these indices, to study, to have more information and quickly accessible information on different topics. So you'll have some more for Sentinel-2 data. For example, the soil composition index, you can have the formula here. Another vegetation index, which is a transformed chlorophyll absorption ratio. And the green soil adjusted vegetation index. And there are a lot more, which is continuously adapted depending on the application. So I can invite you to see this beautiful website, which have a list of all indices, and it's sorted by sensor. So it's quite an interesting database to look at. So we normalized using indices, but when we look at images, we want to have normalized images without compressing information into an index. So here's for optical remote sensing are the 3 steps of corrections. So basically, the first one of pre-processing is geometric corrections. Normally, you won't have to do this because really often space agencies and data providers already did this kind of corrections in order to ensure better geometric quality and georeferencing as well. But if you want to have really dedicated application using VHR, so very high resolution data, maybe it's something you want to have some interest. But for now, I will pass into atmospheric correction, where the idea is to compensate the noise associated to the transfer of the signal through the atmosphere. So there are a lot of modeling, of atmospheric modeling involved in this, in order to have this correction. So it implies 2 things. First, it's you need to know the atmospheric condition at one place, but there are some generic models who can do that. And to know also the direction and angle of observation of the sensor. But also there is very widely known software to do that. And we'll show it a little bit later. And in the end, there are some radiometric correction, meaning that depending on the kind of sensor, is to go through luminance, which is the raw signal, basically, to reflectance. And for SAR, it will be some calibration, for example. So some geometric correction, really quickly. So the idea is to pass from sensor geometry to map geometry. So it needs to use DEM, so digital elevation model, in order to correct by the topography of the surface. For example, here you see the passage from its image sensor geometry to map geometry. And so, as you can see, the idea is to correct from the viewing angle. The differences we can have a displacement of the pixel depending on the topography. So for 200-meter altitude, you will have and a viewing angle of 20 degrees. You will have an offset of 73 meters, so it's approximately 7 Sentinel-2 pixels. So it could be really important. But as I said earlier, most data providers already do this kind of correction. The another part is geometric corrections. So the idea is to get from the luminance, meaning the part received on top of the atmosphere, the part of signal received on top of the atmosphere, to reflectance, which is normalized variable. And so it will use some atmospheric correction in order to do that. There are some interesting software such as Maya, which is developed by the French Space Agency, or Send2Core, which is also widely used for the Sentinel program optical images, which allows to get rid of the atmosphere, TOA, top of the atmosphere signal, and to be at the bottom of the atmosphere and to remove this atmospheric layer, which has a lot of interactions. Yes, so Send2Core and Maya, I will, in order to do some advertisement. So how does it look? It looks like this. So on the left, you have the raw data from a Sentinel-2 image. So it's a top of atmosphere reflectance. And on the right, it's bottom of atmosphere reflectance. You see that you have less effect of the atmosphere. The image is much more clear. And also you have some topographic effects which have been corrected as well. And so it will be much more easier to use in some processes for mapping and land cover mapping, for example. May I ask, can I look? So now we'll go through the SAR remote sensing, and remote sensing is a radar domain. So as Marion said earlier, it's remote sensing. It's really interesting because using active sensors in radar domain allows us to get rid of atmospheric effects, but more specifically clouds, and to see through these clouds. It's really interesting in some areas, tropical areas in particular. Also, there is no worry on the day and night differences. So you can acquire images both day and night. But it requires a lot of more data processing than optical images. And images can be also more difficult to interpret. And we'll see that a little bit later. Okay. So what is radar? And this is, oh, there's another thing, sorry. So radar is used for three main, there are three main kind of radars, such as altimeters, and but we'll not see that as a scatterometer as well. But both are really interesting in each domain. Altimeter are used for example, sea level studies, and scatterometer for meteorological studies. And we'll only look more deeply in synthetic aperture radar and to study the backscattering signal of the radar. INSAR might be of use as well, but I think there will be a dedicated course to for going more in depth in INSAR data, which I want to address here. So the radar, it's only one equation, really. It's this one, where the power received by the antenna is dependent by the transmitted power of the antenna, of course, but also it depends on some parameters, such as the antenna gain, the wavelength, of course, but also, and more importantly, of two variables, which are the distance of the sensor to the surface, Earth, and sigma naught, which is the backscattering coefficient of the surface. And we'll get really interested in that. This sigma naught is dependent of a lot of variables, such as surface roughness, for example, correlation length, the incidence angle, and the frequency of the radar signal, of course, but also of the dielectric permittivity, which is the matter properties of the surface, and it will a lot depend on the surface soil moisture, the sand and clay component, and the salinity of soils. So depending on these parameters, you have different backscattering coefficients. Also, as I showed you here, it depends on the surface roughness, because if there is a smooth surface, there will be a lot more, how can I say this, direct reflection of the light, whereas with the hot surface, there will be more diffuse reflection on the surface. On the wetter media, we'll have a little bit more reflected signal to the sensor, and also a lot of reflection where there are rough surface for wet soils, for example. And here you can see the backscattering coefficient depending on the radar signal and the incidence angle. So for higher incidence angle, there will be, depending on the surface smoothness, where there will be different importance of the backscattering reflection on the surface. So, as I showed you earlier, the backscattering coefficient is also dependent of the wavelength of the radar. So for SAR imagers, there are three main categories of SAR imagery, which are actually 5, but I'll show 3 examples. 5 main categories of SAR images, both in K-bands, which are between 1 centimeter to 2.5 centimeter wavelength, X radar, which are between 2.5 centimeter to 4 centimeter wavelength, C-band SAR, which are between 4 and 8 centimeter wavelength, S-band radar, which is between 8 and 15, and L-band, which is between 15 and 30 centimeters wavelength. So these different wavelengths will impact the reflected signal. For example, here we have 3 examples for X-band, C-band, and L-band. For X-band, for example, there will really few penetration through the canopy, for example, and on the Earth surface, we'll have only the information of the top of the canopy and of the surface. Whereas for C-band radar, we'll have a little bit more of penetration inside the canopy and the soil. And in the end, for L-band, we'll have a lot more of penetration, and they can, for example, we can see trunks inside the forest, and we can see through sands, for example, or dry medium on the soil surface. So depending on the application, you need to select which wavelength you're gonna use. Also, which is really important on radar data, it's the scattering. There are three kinds of scattering mechanism. The first one, which is the rough surface scattering. When there are a rough surface, there will be a diffusion in all directions of the reflected signal. For some cases, there are double bands scattering, which is really interesting, for example, for buildings, because we'll have a lot of more reflected signal using with this kind of band direction when through normal bands. And in the end, there are some volumetric scattering, which will do a lot of diffusion inside the medium, and so a lot of transmitted power. Another variable which is really important in the radar, it's the polarization. So depending on the plane where the signal is sent and then received, you will have some different information you can receive. So when we say, for example, SAR in PV polarization, it means that we send Ragnar signal in the vertical plane and receive it in the vertical plane as well. And for AH, it's in horizontal plane sender and horizontal receive. And depending on this kind of polarization, we'll have different information. For example, for an when you see the difference of horizontal and vertical received, for example, for a tree, you will have for the trunk, for example, a lot more of vertical returns than horizontal returns, as we can see here. And for the crown, we'll have the opposite, because we'll have more less vertical structure in this kind of crown, which will not be the case, for example, for pine trees, because there are a lot of more vertical structure inside the pine trees than the decidual trees as this one. And for really small wavelength, as I showed earlier, we can see also the structure of leaves, which could be of interest for vegetation. And so it can be applied at this wavelength as well. When we look at images such as this one of San Francisco, we can see with the colored composition of the HHVV, HVVH, and HHVV, that there is a lot more of signal received from the buildings here, and you can differentiate from vegetation to urban buildings. So the polarization is really of interest to look at the differences in urban areas. So their example is from ERSA on San Francisco. But this is all good. We can do a lot of stuff with cell images, but as I showed earlier for optical images, you need to have a lot of pre-processing. And I show some of the pre-processing here. First is the terrain correction pre-processing, which is really important because in star geometry, the topography is oriented through the sensor, meaning that if you have here an example, a schematics showing in the direction of the sensor how looks the topography, and you will have three different effects. First is foreshortening, which is you'll see both faces of the mountain, for example, but you will have one much more smaller than the other one because the signal returns first from the faces which is exposed to the sensor. There is also the layer up, that was the layer. So the foreshortening, there's both shadow and the overlay effects, and shadow effects where we cannot see the faces which is not exposed to the sensor. So this kind of effect needs to be corrected in order to have a proper look of SAR images, in order to have map geometry. So here you can see an example. On the left, you have before terrain correction. On the right, after correction. Another correction, which is, so as you can see here, you can have the sensor, as I told you earlier, is on the left, was going through the left. So all mountains are turned into the direction of the sensor. And after the correction, you can see that the slopes seems a little bit more real than before correction. And we are more into the geometric side of the map geometry than sensor geometry. Another correction is radiometric correction, because you see in data providers really often propose to look at to have the backscattering coefficient in gamma naught, which is a normalized reflection by the loop direction. But really often when you look at, no, sorry. So very often you have the sigma naught, sorry, which is, as you can see here, normalized by the ground area, so not by the sensor. And so the problem is you can have a lot of effects due to topography. Whereas sigma naught, it's normalized area projected into the left direction. So it allows us to have less sensitivity to the topography. And some radiometric correction is really of use in order to have a proper map, land map covering. So as you can see here, we are in the Alps. These are the mountains on this part and the plain on the left. And we can remove this difference of radiometry using the radiometric correction I showed it earlier. So in black, you can see the snow here on the mountains. And as you can see, the differences of signal are a little bit decreased, but for very important cliffs, for example, you can see still very important signal which cannot be corrected in this case. Bring back. So there are some ESA, the European Space Agency, manage three kinds of satellites. More on the so more on the science side, which is directly funded and managed by ESA. There are some meteorology satellites which are managed by ESA and for EUMETSAT application. And there is the Copernicus program, which is a European Union funded program, which has an objective to promote science and Earth observation. And so there are a lot of Sentinel, and through this Copernicus program, there is the launch of Sentinel satellites. So there are a lot of Sentinel satellites which have been launched and already here in orbit, and others which will be coming soon. So all these data are provided within our CopPhil near site. Will be provided in our CopPhil near site. So in detail, we'll see the two satellites we'll use for land cover mapping. So the first one is Sentinel-2 satellite, which is an optical satellite. It's optical sensor. It has some particularities. First, as it is optical sensor, it needs to be sun-synchronous. So it is on the orbit at 700 kilometers above the Earth, and it visits each part of the globe at 10:30 a.m. each morning. So we are 20 minutes late to say hi to satellite sensor. And it's a 10-day revisit cycle for each satellite. As there are two satellites, it's 5 days between each acquisition maximum. And there is a 290 kilometer field of view, so a very large acquisition area. And as we discussed it earlier, there is three spatial resolution of 10, 20, and 60 meters, depending on the spectral band. So as you see on the table on the bottom, there are 4 Sentinel-2 satellites planned. The Sentinel-2C will have been launched in September 2024. And it was meant to replace Sentinel-2A, which is now almost 10 years old. But apparently there is some question to let it in orbit and to continue acquisition, but and so to maybe have a more frequent revisit cycle. But everything is not set in marble, so wait and see. Yes.
And so is that at 98%.
The question, there is a question in the audience asking if it's a descending acquisition. Yeah, it's local time. Yeah. So the question was actually on which time zone we have the when is acquisition and at which time zone. So it's local time. So for Sentinel-2, there is the specification for the satellites. So you see here the sun synchronous example of acquisition. And this slide, you'll see Sentinel-2 spectral bands compared to Landsat 7 and 8 spectral bands. So there are 13 spectral bands. On this area here, on the bottom, the band 2, 3, 4, and 8 are 10-meter resolution. So for blue, green, red, and near infrared, there are very small spectral band here, really related in order to better see differences in near infrared for vegetation, for example, and in shortwave infrared as well. And 1, 9, and 10 are more broader spectral bands. And as you can see, they are located whereas there are a lot of absorption of the signal from the atmosphere. So it's meant more to study the atmosphere and aerosols and so on. And there is a 12-bit radiometric resolution for this sensor. As I told you earlier, data provider gives the data at different levels. So it meant that it is different levels of pre-processing of the product, but the most used are level 1C images, which is top of atmosphere reflectance, and level 2A, which is bottom of atmosphere reflectance. So depending on the suppliers, you will have different level accessible. And level 0 and level 0 are not available because it's directly at in the sensor coding under the sensor code and data. So it's not available, but starting from 1A, 1B, 1C, and 2A, it's available. But the most interesting for uncover use is level 2A, which we'll use later. For SAR imaging, we'll use mostly Sentinel-1, which is in activity since 2014. Sentinel-1A is on orbit since 2014. So it's a C-band SAR instrument, meaning that you have a wavelength of approximately 5 centimeters. So it's a near polar orbit, meaning that it's down dusk acquisition at 398 kilometers as well of altitude. And it's 3 days repeat for one satellite. So for the entire constellation, it's a 6-day maximum time of revisit between two acquisitions. Since Sentinel-1B have a failure, Sentinel-1C, which has been launched in December 2024, now is almost in service, I think, or will be soon. But thanks to this satellite, we'll have again a 6-day acquisition between maximum time of revisit. So there is also different SAR modes. which are the interferometric wide swath, the wave modes, sweep maps, and the extra wide swath. So with different resolution and cover, but for land cover and surface application, for most of them, we'll use the IW interferometric wide swath mode, and it has a swath width of 2,050 kilometers. With polarization HH plus HV or VV plus VH, and a range and azimuth range of 5 meters and azimuth of 20 meters, which means basically that we'll have once sampled a resolution of 20 meters. Yes. So some example of the satellites I showed you. So here it's a backscattering coefficient of the clouds occurring in Greece in 2023. So it's not Sentinel-2, but Sentinel-1 gamma 0. The label is wrong. But you can see in black, it's with a very low backscattering coefficient. It's flooded areas. And when you look at the Sentinel-2 images, which is 1 day away or 2 days away, I don't remember exactly, you can see the area covered by the flood, which is quite important. So it's covered by the question someone asked earlier, that there is some additional information you can add with both Sentinel-2 and Sentinel-1. In this case, we have quite a chance because we have an optical image chance, not for the people flooded, of course. We have the flooded area we can be seen with an optical images, which is not always the case. Using Sentinel-1 data, we can also track all spills and all pollution. So you see in VV polarization, you have a better view of the old spill than in VH polarization, which has no effect on this polarization on the old spill. And one last example, using Sentinel-2 data, Sentinel-2, Sentinel-1 data. It's to manage and to see the deforestation and also overplantation. So you see here there are some on top. It's a Sentinel-2 images in color composition using near infrared in order to see overplantation here in this area. And 2 years later, so some places which has been cutted. There are some tree cuts here in order to plant rubber. And you can see also the newest and smaller tree on the rubber plantation here. So do you have some question on the Copernicus satellite sensors? Maybe online? Okay. So now we'll look at data processing in order to have our land cover map. So we'll cover this part in 2 parts. The first part is more about generalities and describing some the land cover, what it is, and the methods to produce a map. And the second part is more into the toolbox we use in order to do land cover mapping in the CopPhil service, which is IOTA 2. So let's go and let's see what is it. So first, some generalities. So land cover, as you can see, some example on the right here are the observed geophysical properties and cover on the Earth surface. And it's different of land use, which is a description of how people use the land and the socio-economic activity. Because each from a sensing, it's much more easier to look at the geophysical cover because we have some information which can be visible from a satellite than the land and socio-economic activity, which is a little bit more complicated or need an external data set to do so. To map land cover, there are a lot of techniques using remote sensing images. But first, so we will go into the definition a little bit more in details. There are some classification system that exists in order to differentiate two classes between each other. Here we will have an example in this chart of the LCCS developed by the Food and Agriculture Organization, FAO, which is a classification which is made in two steps to describe each class. First, it's a more dichotomous phase where you have to choose vegetated, non-vegetated, and then the place where it takes place, if it's terrestrial, aquatic, then if it's artificial, natural, and then a second level of classification, which is a modular phase with three kinds of attributes. For example, some properties like pure land cover classifiers, some attributes which are more related to the environment, such as, for example, climate, altitude, and vegetation, and some specific attributes. So with this kind of diagram, you can create your own classification nomenclature that you use for land cover mapping. And for example, most of the land cover use this land cover classification system from the FAO. So to continue into nice diagrams, let's talk about so automatic methods to produce LC maps, because it exists some methods using visual interpretation, and but that's not of our interest here, because we all want from remote sensing images to have an automatic mapping of land cover. And we have two main classes of mapping: supervised learning and unsupervised learning methods. So when there are no learning, the advantages are there are no a priori knowledge required, so no need for field data or data for validation and training. But the problem is it's really often related to spectral grouping, so very close to detect pixel with very close signature. But the problem is this grouping doesn't always correspond to a class. So that's why we, in this kind of problems, we really often use supervised learning, so machine learning or deep learning methods. The advantage is the methods are not independent, so meaning that you will not be influenced by the statistical properties of the image. But the problem is it requires a lot of training data. So so that's a big problem, and we'll go into this just later. So as common supervised learning algorithm, there's some classification trees such as neural network sensor and support vector machine, for example. So when we talk about samples, dataset, training samples, so we'll really often use in situ measurements of or photo interpretation from VHR images, which allows us to have really high resolution samples, but also some external sources such as GIS sources. Here I put some example from the French land parcel identification system, because there is the equivalent of IRS, so the fiscal authorities in France have a registration of each agricultural parcel and what has been cultivated on it. And so it's it's public free. So you can use it to train some data set and see and do some classification basically, but not every country has this kind of system. And there's also some more larger programs such as the Korean land cover, which is a European land cover made from visual interpretation of remote sensing images. And here you can see the urban classes from the Korean land cover dataset and from the French Mapping Institute as well in yellow, and to compare the two datasets. So to do this kind of reference dataset, some advice is to select the center of each object in order to avoid border effects, which can be affecting the training and the classification. Select large surfaces in order to have some pixels, and to have an homogeneous distribution of samples over the study region, and of course to have a high number of sampling polygons. So now that we've been talking about more general methods, I will describe you the IOTA 2. So IOTA 2, what is it? I will spare you the French name of IOTA 2, but it's in English, Infrastructure for Land Cover by Automatic Processing Incorporating Overall Toolbox Application. So it's IOTA. And IOTA 2, it's a toolbox created by CESIO, which is a CNES-related laboratory. CNES is a French space agency. And it's really interesting because it's been used since 2016 on an annual basis in order to do the French land cover map. And so it's continued to be fitted and improved over the years. And the most interesting thing about this toolbox, so it's a tool made for land cover mapping and processing. And it uses Sentinel-2 datasets as well from time series, as well as Sentinel-1 datasets. But it also can use some auxiliary data such as DMs and other raster data. You can feed it in order to do the classification. And it's robust enough to do the classification over one entire country without big problems. So to use several Sentinel types altogether, it can take also in account the climatic difference, eco-climatic difference between geographical areas. And so it's an automated process for classification because it relies on machine learning algorithm, and in particular random forest. you can also choose the sampling strategy for training. And the end, when you have some outputs which can be vectorized if you want, and also there is some validation already integrated into the chain. So you see the example on the left with some example for here for some different runs on IOTA 2 here for the same land cover classification. So IOTA 2, more in detail. So there are three big modules in it. So there is data preparation for the reference and the reference data and the images. Also, there is a part where there is a supervised learning from the training data set. And in the end, there is a map production. I will not go into details right now of each step of the process, but we'll look at some of these. So first, we'll look at the data process, the data selection. So as I told you earlier, IOTA 2 is based on a study of time series of Sentinel-2 images and Sentinel-1 as well. There will be a selection of the so-called. There will be a use of, for example, Sentinel-2 images of each image's relation. We will be stacked into a time series queue, including the cloud cover, which been already implemented in the level 2 images. That's why it's really important to have level 2 images for Sentinel-2. And for example, on the year, on the Luzon area for one tile, you can have around 50 images for cloud cover, less than 30%. So we select first images with a low cloud cover. We stack them. We can create some indexes in order to have a temporal stack of additional information and add external data sets such as DEM. Then once we have all this data, we'll have a time of, we'll study each pixel one by one in order to have a time series and taking into account, of course, of clouds. So data with pixel with cloud masking will be not taking account in the time series. Sorry, only the value at the time of the cloud cover will not be taken in account in the time series. So you only have the reflectance time series on one particular pixel, such as this one. And in the end, we'll have the processing in order to do the land cover maps. So it's a pixel-wise approach, and it's a temporal interpolation, and it will use the phenology differences of each classes in order to do the classification. So there will be specific time series depending on land cover classes. For example, for buildings, there will be a very low NDVI all along the year, whereas for vegetation, it will change a lot. So here you have NDVI example for one crop. So for example, there is all along the year the crop grows, then it's cutted, so there is a big drop in NDVI. Then there is a vegetation regrowth just after that, and a decrease because in Europe there are some winters, so there is a drop in vegetation at that time, or there can be some flowering at that time also, which can decrease the NDVI. So on the left here, you can see the difference for several classes of crops, for example. there are corn, there are sunflower, soy, wheat, barley, with different phenology and for each cover. And on the right here, we have for I don't remember, it's rapeseed. For rapeseed, all the pixels, all the time series. So you have the spectral variation for one classes. So what you can see using the reference training data. So we'll base the study of this spectral temporal spectral data. And also it's another example here. It's color composition for, so in red it's NDVI for January to April, blue to September to December, and green from May to August. So for example, you have the peak of NDVI in green in May to August. So you see some parcel here where there are a peak of NDVI at that time. So you can differentiate quite easily the different crops on this kind of and different non-cover types on this kind of image. And on the right, you have Sentinel-1, also cloud, color composition with the same legend, and you see that there is more bluish composition here. There is an increase of backscattering coefficient in September, December. It's often in Europe, it's a plumping season, so there is bare store, so with a much more higher backscattering coefficient at that time. So you can see that both in Sentinel-2 and Sentinel-1, we can have a very useful information for the crops using temporal information. So once we have our images, we can choose the sample selection. So here's an example. Once you for one reference data polygon here, and here it's each point represents a pixel into the Sentinel grid. And for the training data, you have the possibility to choose different sampling, so which will be important in order to select the data you use for the machine learning training. So, for example, there is a possibility to do a random selection. You see here it's a 50% random selection. And you can have also a periodic selection, meaning that you have a more proportional selection on all these polygons. You can also choose to have a constant number of pixels for training for each class, for example, or use a percentile. And in the end, you will also, for each class, define the number of pixels you want to use. So we go now to, once we have our training data and the images, our spectral profiles within the year, you can use a machine learning algorithm, and the one which is implemented for land cover mapping in IOTA 2, it's the random forest, which is an algorithm introduced in 2001. And it has really a lot of advantages. It's interesting because it's quite robust for label noise overfitting, meaning that if you have some error on the labeling at first for the reference data, it can overcome it. Also, it's also it's really interesting in order to because it's quite robust for big data sets. So in terms of the dimensionality, it's not a big problem, and it's due because it has a really low computational complexity, and it can be distributed, so it can run on several cores at the same time. And how does it work? It's free and non-linear model because it's used different decision tree, decorrelated decision tree, and average value. So if you have some example on the training method, for example, here you have two variables, and it will for one tree create two nodes in order to try to select the best each classes and to minimize the number of nodes. So, for example, we'll put a threshold here in order to have first selection, and the idea is to have always one node separating, which can separate both a mix of of several classes and one classes, and so there are some parameters within the algorithm. So it's a number of tree, of course, and here also the number of nodes you go into the classification. The more tree you have, the more detail you have on your classification, the more good it will be, but it will take longer, and but also it will take longer. And the number of nodes it's allows to have a more firm separation in class. So it's a bootstrap method, meaning that for training, it will have a random selection for the training set for each tree. So the big interest is that there is decorrelation between each tree, whereas if you use the same training sample each time for each tree, it will have some correlation, and so will create more issue concerning the accuracy of the model. So it will allow confidence measurement for each model. So you can, there are some index in order to find the best fit between two nodes. There are some different, here it's a Gini index which has been implemented. So here's an example of some trees. So some takeaway message for random forests. So it's several decision tree. It's an ensemble of classifiers, decorrelated classifiers of decision trees. They are built randomly, selecting samples for replacement. So there are two important hyperparameters: the number of decision trees, the number of variables used to split the decision nodes. And here in this method, about 1/3 of the samples are used for assessing the confidence of the trained model each time. So once we have our machine learning algorithm, now it's time to scale it up by looking how to apply it on a larger scale, for example, at a country scale. So the problem is that when you have a machine learning algorithm, the training will require to be really global in order to classify correctly the whole area, and to take into account the spectral, the variability of the reference data within the whole area. it's not always possible because you can have some differences due to meteorology and geographical attributes that create some variability inside the reference data set. For example, I don't know, for example, a coconut tree in Mindanao in Luzon will not have the same spectral or temporal signature over time between these two places. So the main idea of IOTA 2 is to integrate some contextual information, and one of them is to integrate spatial integration in order to take into account this variability over the different region of the country, for example, and to merge the different classification in the end. Another possibility is also to increase the accuracy of classification. It's a method created by the people for the IOTA 2 algorithm, which is called autocontext, which is based into the study of an object-based level. So, for example, in this example, it performs segmentation and superpixel segmentation, and there will be first round of classification to see what are the classification labels in each superpixel, and regarding the main categories in each superpixel, tries to refine the classification in several runs, and to use the neighboring superpixel class in order to increment and to add more details into the classification. So it's another nice feature which is integrated in order to improve accuracy. Some example you can have that already Marion showed earlier. So she already showed small details around this part, but here is the land cover map of Luzon region with produced using IOTA 2. It still needs to be more refined because it's a first row of processes. But here you can see the 11 classes are already used by NAMRIA on their own land cover classification from 2020 in Luzon region. So that's the first many products you can obtain using IOTA 2. And also you will have the confidence map, which is produced by the random forest algorithm, as I showed you earlier. So in white, it's the most confident classified pixel, and in black, it's the pixel with the less accurate classification. Another subproduct you can have is the pixel validity map. So it's the number of observations we can have on a time series. So you can see that in really cloudy places, you will have a low amount of observation, whereas, and you can see also the difference between tracks of Sentinel-2. So it can be of use to see on the classification the errors coming from cloud covers and tracks and ties. And as I showed you earlier on the map, some of you maybe noticed that there can be some of bad classification for some classes. But in IOTA 2, there is the possibility to have some validation metrics, such as overall accuracy, precision, recall, F1 score, and points kappa. So for overall accuracy, since the proportion of pixels correctly classified on the whole map. For precision, it's the proportion of partly predicted cases from all was predicted as positive, and so on. That's really interesting in order to see the accuracy. And these validation metrics are made from the part of the sample which has not been used for training the random forest algorithm. So for example, you can decide to use 70% of your sample for training and 30% for sampling for validation, which been the case in this example. So here we have an overall accuracy of 0.73 and the kappa of 0.63. So, and the confusion matrix here with the predicted values classes at the here and the reference value on the left. So everything in agreement will be on this diagonal with the number of pixels in each case. And you can see in this example that there are a lot of disparities in the example I showed earlier. And for some places, there will be a lot of good classification. But for some, for example, for open bind, there are really a low amount of good classification in this class because there are a lot of missing with built-up classes. Also for Russian maps, there are a lot of confusion with open forest, for example, which is normal because they are very close classes. And also for inland water and fish ponds, there are also a lot of confusion, as you can see it. So here's the validation part. That too, you can look at the documentation online. So here are the main four websites where you can see some information about IOTA 2. First is the documentation of the toolbox itself. Of course, there is a tutorial in English as well. There is the CESQ, so the laboratory works on these processes, which has a blog with a lot of info. Some articles are in French, but most of them are translated in English. And in the end, everything it's based on the CopPhil toolbox, which is toolbox made by the French Space Agency in order to create some remote sensing application. And it's also, as the two software are related, and the IOTA 2 relies on the OTB algorithm, I also gave you the link to the CopPhil toolbox documentation if needed. Thank you very much. If you have some questions. Or maybe online.
Hello, Etienne. Question here, I think, from the online participants. Can you hear us? Hello?
I cannot look at the question which you can. There is one question. Okay, that's it. Okay. Okay. So maybe Nicola, you can talk, and then I will put a micro on.
Yeah.
Yeah.
Thank you. I'm also bumping this question from earlier, so give me a moment.
Okay, Carla, there is no, actually the sound of the computer is not repeated in the room, so I think maybe
There was a question earlier about the example I showed on the banana application.
Okay, there's an example on the question about the banana plantation. I would like to know more about the process, and can you kindly explain on the workflow that was involved in the generation of the density map?
The density map.
Yeah, but actually it's not our team who work on this, so I cannot be of much use on this. But I think it uses Sentinel-2 data. But exactly the details and which algorithm has been used to produce this map, I'm not aware of, unfortunately.
But
yeah, Marion will maybe answer you.
Just to complete, I think, as we mentioned, this is like about the land cover, and we'll have some specific sessions about the crop where you meet the experts working on the crop mapping, so they might be able to answer this question. More question?
You have more questions, maybe? Okay, there's Marion will take the show now and conclude.
All right, just 2 slides to conclude. This is the link again to the Moodle platform. So I leave it for now, but you will have it. We can share this again. So all the courses that we presented today, so the slides and the video will be found under this Moodle platform. So if you register to it, you can then access to all this content. You will also find there the recording of the training one, which happened in October, November 2024, where we exposed more about the context of Copernicus program and providing maybe some background on the CopPhil project that we did not really talk to today. So I invite you to register and to look for the content on this Moodle platform. And then just to provide you some ideas on the coming courses. So now we are doing the fundamentals for land cover. Following this session, it will be there will be a practical course, essentially on the last part of the presentation that we have today. So on the IOTA2 processing. So really going into more details in the practical use of the data, so putting your hands on the calculations, and then followed by an application course that will be probably end of July, beginning of August. So the second one will be probably first week of June, and we'll give you some details about the dates later on. So as I mentioned, we also have these 2 sisters courses on forest and crop. So the first theoretical course for forest and crop will be both online, and we have the dates already, so we can take this date, and we will be sending some invitation and links. So for forest, the fundamentals theoretical series course will happen on Tuesday, 11th of March, from 2:30 to 5:30 in the afternoon, because we'll have the experts from Europe presenting this course. And for the crop, it will be on the Thursday, 13th of March, 3 to 5:30. Okay. Then I will just leave this again, but I've showed this during the break, so I think you probably have the information. If you don't, please just send us an email. I think you also saw our emails, and don't hesitate to contact us. And I think that's it. I will